Understand a question, a numerical problem on transition of states by electrons in an hydrogen atom. The question says that what are the frequency and wavelength of a photon emitted during a transition from n is equal to 5 state to n is equal to 2 state in the hydrogen atom. So what we're given is it's all about hydrogen atom. It's all related to Bohr's model of hydrogen atom, the Bohr's theory of hydrogen atom, and whatever Bohr has found out, and according to theory put forward by him, we're going to solve this problem. They've given that the electron there's a transition of electron from n is equal to 5. So n is the principal quantum number, and it denotes the stationary states, the possible stationary states, the permitted stationary states that an electron can have while revolving around the nucleus. So the electron was in fifth state, where the quantum number is 5, and it comes back to the second state, to number 2 state. So while doing that, the electron will some amount of energy will be released in the form of electromagnetic waves. We need to calculate the frequency of the electromagnetic wave that is released, because the electron will have more energy when it was in n equal to 5 state. So when it comes back to the n equal to 2 state, it will have less energy. So the excess energy will be released, will be emitted in the form of electromagnetic radiation. We need to find out the wavelength, the frequency, and the corresponding wavelength of that electromagnetic radiation. So what will happen is, so there is a difference for principal quantum number with n is equal to 5, and the principal quantum number with n is equal to 2. There is a difference in energy. So that difference in energy, delta E, is equal to the final energy, the energy in the final state minus the energy in the initial state. So what will be the energy in the final state according to Bohr's theory of hydrogen atom? The Bohr's model of hydrogen atom is equal to minus RH, the Rydberg constant of hydrogen atom, divided by NFS squared. This is the principal quantum number. So energy in the final state minus energy in the initial state. Energy in the final is which state? It will be, final state is this. This is the initial state. So we'll put NF is equal to final, that is 2, and Ni, the initial state, the initial principal quantum number, Ni is 5. But before doing that, there was a negative sign in the relationship of or in the formula, or the relationship of finding the energy when an electron is in its stationary state is equal to minus of RH divided by NF by the square of the principal quantum number, corresponding principal quantum number. So this is the expression. There was a minus sign here. This minus sign is maintained here. So while simplifying, what comes? This will become positive while multiplying. So let's put this before and this after, right? So that means the RH is common in both the terms. So we take out the RH common. What remains is Ni square minus NF square. So this is what? This is initial quantum number minus final quantum number. Initial was 5 minus the final was 2. So it becomes 4 minus 25 in the numerator, which will be negative. So it's negative 4.58 into 10 to the power minus 19 joules. So what does this negative mean? It means that there was more energy when it was in initial state, when the atom was in the fifth state. So when it come back to the state of state number 2, so there was the excess energy, it got in it. So this minus means the energy was more in the initial state. This minus this is become negative. It means there was more energy here initially when it was in n is equal to 5. So when it came to n is equal to 4, there was less energy. So less minus more will be negative. So this is what it means, negative sign. And this much energy will be released. So this much energy will be released according to Max Planck. Now we are coming to the question. Now we are going to calculate the frequency. We have calculated the difference in energy of those two states. The energy when it was in the fifth state was in the fifth state, and the energy when it is right now in the second state. We have calculated the change in energy, the change in so it has that is a value for minus 4.58 into 10 to the power minus 19 joules. Now we will through Max Planck theory, the Max Planck theory in which the in which whatever the electromagnetic radiation is comes out, it is quantized. It comes in terms of packets, in energy packets called photon, and the energy of one photon is equal to the frequency multiplied by the Planck's constant. Okay, the value of Planck's constant is 6.626 into 10 to the power minus 34 joules again. Now you can easily calculate frequency when you know the change in energy. This energy is the energy that will be released, energy that will be possessed by each photon, and it can be expressed in terms of its frequency and the Planck's constant. So if you want to calculate the frequency, then you will divide the energy involved, energy in one photon divided by the Planck's constant. And this has come when you divide this by Planck's constant, you'll get 6.91 into 10 to the power 14, since it is frequency hertz. So 10 to the power 14 hertz means this one is like visible. It corresponds to visible spectrum, visible region, 10 to the power 14 hertz, right, of electromagnetic spectrum. Now we have calculated the frequency. What about the wavelength, that corresponding wavelength? So according to James Maxwell's theory of electromagnetic radiation, the relationship between the velocity of the electromagnetic wave c, which will be constant for all the electromagnetic radiation, is equal to frequency multiplied by its wavelength. So if you want to calculate the wavelength, divide the velocity of the electromagnetic wave by the frequency. The velocity of electromagnetic wave is the same as the velocity of light, because light is also an electromagnetic wave. It is 3 into 10 to the power 8 meter per second in vacuum, divided by frequencies. Just we have calculated 6.91 into 10 to the power 14, so it comes to 434 nanometer. Okay, one more thing that you can notice over here. This belongs to this series of the wavelength or the frequency. This transition, it is called Balmer series, discovered by the scientist Balmer when n is equal to 2. So from any state, any higher state, n equal to 3, 4, 5, 6, 7, 8, 9, 10, when it comes back to the second state, the series of the spectral lines will be called Balmer series, and its corresponding energy or frequency can be energy, frequency, and the wavelength can be calculated in this manner. Hope it's clear.